Welcome back, everyone, to Code Meets World. And today we're going to be looking at another problem in the NeetCode 150. Last time, I completed the balanced binary tree problem. And in this video, we're going to tackle the same tree problem. Again, the fifth easy problem in the trees category. One more and then we'll be finished with all the easies in this one. So let's see what we have this time. So, given the roots of two binary trees, P and Q, write a function to check if they are the same or not. Two binary trees are considered the same if they are structurally identical and the nodes have the same value. Okay, so that's interesting. Let's see what structurally identical means. So in this case, we have 1, 2, 3, 1, 2, 3. Those look the same, and it returns true. So those are the same. That makes sense. Example 2. So these trees both have a root of 1 and a child of 2, but this one has it as the left child, this one has it as the right child. So this one's false. So even though they have the same root with one child and it's the same value, this is false because they're not identical. The children are on different sides. Okay, in example 3. 1, 2, 1, 1, 1, 2. So this should not be the same because the 2 and the 1 are switched. And yeah, that is indeed false. The trees are pretty small, so they'll only have up to 100 nodes. Okay. All right, so this is a really interesting problem. Let's jump down to the whiteboard and see what we can figure out. Okay, so there's a couple of different things that we can think about here. I think that one of the ideas that's coming to mind is the idea of a full tree, or maybe it's a filled tree. If anyone in the comments wants to tell me that I'm wrong and there's another word for this, do let me know. But what I mean is, I think to solve this problem, we need the trees to be completely full, meaning there are no gaps. No gaps in the tree. And let me illustrate what I mean by that. So if we look at this first case here, this is what I would call a full or filled tree, because it doesn't have any gaps in it. Obviously there are null children down here, right? But without those, the tree is still perfectly full. I think it's easier to see this if I show you an example of the opposite. So this one here is not full, right? Because look, it has the structure, neither of them are full because they have this structure, and to make it full, it's missing one child on each side. And so I think it would be really hard to figure out if these two are the same without first making it full. And again, this one down here is a full. And once the tree is full or filled, I think the way that we would figure out if the two trees are the same or not is simply by traversing the tree using one of our 3 tree traversal algorithms, pre, in, or post order, and simply putting all of the values that we encounter into an array and seeing if they're equal or not. What I'm not completely sure of is if I want to do pre-order, in-order, or post-order, so I might need to do a little bit of a test here. So let's think about it like this. If I call in each of these examples, the first tree, tree A, and the second tree, tree B. What I think I can do is make an A and a B array. And I'll start out with a pre-order traversal. So a pre-order traversal, and I'll link a video at the top here if you would like to look at what each of the traversals means. I explained that in a previous video. So if we do a pre-order traversal for tree A, it would go in this order. We'd first start there, then go to 2, then go to 3. So we would have 1, 2, 3. And of course, this would be the same for tree B. We would start at 1, then 2, then 3. These trees are identical, so I'm just showing that they're actually the same. If we do an in-order traversal, we would hit here first, then 1, then 3. So that would give us 2, 1, 3. And obviously same for this one, 2, 1, 3. And then I need a different color. If we do a post-order traversal, we would get 2, then 3, then 1, and obviously it's the same for both. 2, then 3, then 1. So obviously here, they're all the same. So that doesn't help me very much. But we're going to do the same now for this next one. And this one I'm really curious about. So instead of looking at the trees over here, I'm going to look at these ones here. Because again, I think the problem lies in that if I do my traversals on these ones over here, I think they're just going to give me the same value, even though they're different, because I need to fill in these missing children. Let's see if I'm right. So for a pre-order traversal, and let me draw, no, actually, let me not do that. I'll just do it on these ones here. For a pre-order traversal, we would hit 1, then 2, then null. So I gotta write in A, B. For the first tree, this would be 1, then 2, then none for that empty one. Whereas for the other one, it would be 1, then none, then 2. So notice how those are already different. These two are already different. That's a good sign, because that means that by doing this algorithm and filling in the empty ones, I can successfully show that these should be false. So pre-order traversal is definitely a possibility. Let's see for in-order. For an in-order traversal, we would go 2, 1, none. And then for the other one, we would go none, 1, 2. Okay, those are also not equal. Whoops. Those are also not equal, so that's good to know. And then lastly, for our post-order traversal, we would have 2, none, 1. And then we would have none, 2, 1. Okay, so they're all not equal. So that's great. I think I can use any of them then. I think the secret is that, and I'm not even going to fill in this last one. Oh, wait, actually. 2, 1, 2, 1, 1, 1, 2. No, okay, it's the same for all of them. Yeah, okay, sorry. So I think I've proved that I can use any of the traversals to make this work, as long as I fill in and make the tree full. So hopefully this makes sense as far as my algorithm, everybody. I know this has been a long explanation, but I think it really helps me understand what's going on here. So I just need to fill in these missing children to make the tree full. And then I can just traverse the tree any way that I'd like and compare the arrays at the end. And if they're equal, then the trees are the same. And if they're not equal, then they're not. Right. So let's flip back up to the actual code here. Great. So where do we start? Well, I think what we want to do is make our arrays. So I can call them, just like I did in the notes, I'll call it A and B. And then we're going to have to traverse the tree, right? So I can say, I need to make a traversing function. So we'll say def traverse, and this will just take a node. I think I'll do a post order traversal. So again, we'll want to traverse over left subtree. We'll want to traverse over right subtree. And then we will want to visit the node. In this case, visiting the node should be as simple as adding value to array. So that brings up a good point. I think I'm going to need to pass the array through the recursive calls so that we're always updating it. Because remember, all I'm trying to do here is traverse the tree, add values to the array as I encounter them so that we can compare the arrays at the end. Basically, I need to traverse tree here. So I'll put to do, since I haven't written that yet. Actually, I can just write it now. I can just say traverse. I will put in the first tree, which is P. Remember, I have 2 trees. So if I traverse P with array A, I will do the same. I will traverse tree Q, right, with array B. And then I can just say return A equals B. So right, this is just like I showed on the whiteboard. And I know I haven't filled in this function yet. But we'll make 2 arrays, A and B. We will traverse tree P, which is the first tree, with array A. So we'll basically add all the values of P into array A. We'll do the same with Q. We'll traverse it. We'll add all the values to this B array. And then we'll compare A and B. If they're the same, we return true, if they're the same tree. If they're false, this will return false, meaning they're different trees. So now we just have to fill in the traverse function. Adding the value to the array is as simple as saying array dot append node dot val, like that. Traversing over the right subtree is as easy as saying traverse node dot right, so the right child, and then we need to keep passing in the array each time. And then traversing the left subtree is exactly the same, node dot left and array. Fantastic. So this is quite close, but I don't think it's going to be perfect yet because I haven't added one part. Yeah, and this shows the same thing. So I can't call this on none. I need to handle the case where I encounter something that is none. Because remember, my entire algorithm works on the premise that anytime we encounter something that is none, we need to add none to our array. Remember that from the earlier part of the video with the whiteboard. So if not node, meaning if it's none, I think I just want to add the value none to the array. Array.append none, like that. And then I think I just want to return, right? Because if it's none, I don't want to do anything else. I just want to add none to the array and then come out of that recursion step. So let's see. This feels like mostly everything that I need. Fantastic. So that has worked quite well for all three. And here, everyone, let me show you what these actually are. So let me print out, to show you that this is working, let's actually print out A and B for each case. So for case 1 here, and you might be looking at this going, whoa, what's happening here? But I think, yeah, so look. So for my post-order traversal, we come down the side here. Then we come to these two none children nodes, right, that are down here. Sorry. And we add both of those. Then we add the 2. Then we snake around here. We come down underneath the 3 and add these 2 nodes that don't exist. Then we add 3, and then we come up to 1. So yes, it's unnecessary to add these none nodes down here. I wasn't thinking about that when I wrote the code, but it works in this case. So let's move on to the second one. So yeah, you'll see here that they're different, because in this case on the left we hit 1, or if we're doing a post-order traversal, we would come down and we would hit the 2 children nodes of 2, which we show here. Then we hit 2, then we come up and around and down. We would hit this none node right here, which we add, and then the 1. But on the right-hand side, you can see that it's different, because we would hit this none node, then children, or child, node 2's none children. So we get 3 straight, then the 2, and then the 1. Hopefully that makes sense. But it seems to be working, so let's go ahead and submit. Fingers crossed. All right. So that worked. 25 milliseconds. I don't know why that's so slow, but maybe it's just because of these solutions would be pretty interesting to look at, but I'm not sure why that's so slow. I think it's a very, very intuitive solution, so I'm happy with that, because again, that's all I'm worried about is writing something intuitive that makes sense to me and hopefully makes sense to everybody else as well. Thanks again for watching, and I'll see you in the next video.